Learn Efficient Pharmacology, Pharmacokinetics Part 11, Renal Excretion. Through metabolism, a lipid-soluble drug is converted into a water-soluble metabolite. Since it is water-soluble, it can be dissolved in urine or other body fluids and be easily excreted. But for this, the metabolite has to first move out of the hepatocyte by crossing the lipid bilayer. This is a challenge because the metabolite is now water-soluble or polar and not lipid-soluble. We know that polar molecules cannot cross the membrane by simple diffusion. We have seen the solution to this problem in the previous videos: membrane transporters. Hepatocytes have transporters on the canalicular and sinusoidal membranes. So the metabolite can either move through the bile to reach the intestines or through the blood to reach the kidneys. The kidneys are the major excretory organ, so let's focus there. The structural and functional unit of the kidney is the nephron. Its parts and vascular supply are shown here. Pause the video if you need to. In addition to the metabolite, the unmetabolized drug also reaches the glomerular capillaries. To be excreted, these molecules have to first move into the tubular lumen. How is this possible? The first site where this can happen is the glomerulus. Here, the drug can be filtered into the Bowman space. This is glomerular filtration. Here, the molecules have to cross the glomerular filtration barrier. Logically, such molecules have to be smaller than the pore size of the filter. But being small is not enough. This is because the glomerular filtration barrier is negatively charged and therefore repels negatively charged molecules. So, despite being small, negatively charged molecules may not be filtered. If size and charge are important factors in filtration, can protein-bound drugs pass through this barrier? No. Plasma proteins that bind drugs are usually large and typically negatively charged. So, the protein-bound drug is not filtered at the glomerulus. By now it is obvious that not all drugs and metabolites are filtered at the glomerulus. The unfiltered molecules move through the efferent arterioles to reach the peritubular capillaries. To move the drug and metabolite into the tubular lumen, the body first utilized glomerular filtration. This process did not use any additional energy, that is, it was passive. But here, to move the drug and metabolite from the peritubular capillaries into the tubular lumen, the body uses tubular secretion. This is an energy-dependent or active process. Therefore, this requires membrane transporters. This process has a few advantages. Since it is an active process, molecules can be transported into the tubular lumen even against a concentration gradient. In addition, transporters can be selective, that is, transport only those molecules that must be excreted. Transporters we know are capable of easily transporting charged molecules too. These include the negatively charged anions and the positively charged cations. It is no wonder that the organic anion transporters or OATs and the organic cation transporters or OCTs play an important role here. Other transporters such as MRP, MDR1, MATE are also involved in the movement of the drug from the peritubular capillaries to the tubular lumen. Pause the video to see in detail how this transport takes place. Thus, two processes move the drug and the metabolite into the tubular lumen: glomerular filtration and tubular secretion. These two processes have been compared here. Pause the video to see the details. Why is it mentioned that protein binding does not affect tubular secretion? There is an explanation for this. The transporters secrete the free fraction of the drug. And when the free fraction of the drug in plasma falls, To re-establish the equilibrium between the free and bound fractions, some of the bound drug dissociates from the protein and becomes free. These newly freed molecules continue to be actively secreted into the tubular lumen. This is why protein binding is not considered to influence tubular secretion. Thus, through glomerular filtration and tubular secretion, the drug and the metabolite reaches the tubular lumen. Now, the drug concentration is higher within the tubular lumen. So, as the drug moves through the tubular lumen, due to the concentration gradient, it can move back into the capillaries by simple diffusion. That is, it can be passively reabsorbed. So, if molecules reaching the tubular lumen are reabsorbed, then wouldn't glomerular filtration and tubular secretion be pointless? No. If you remember, it was to prevent this reabsorption that the body metabolized the drug into a polar molecule in the first place. Large polar molecules cannot cross the membranes of the tubular cells by simple diffusion and therefore are excreted. In addition to large polar molecules, ions too are unable to cross the plasma membrane by simple diffusion. So, a simple strategy to enhance the excretion of a drug is to increase its ionization. How can that be done? In the previous videos, we have seen that many drugs exist as weak acids or bases that ionize in solutions. Here, a change in the hydrogen ion concentration can affect the degree of ionization. Consider the example of an acidic drug in the tubular lumen. If the hydrogen ion concentration decreases, that is, if the urine becomes alkaline, more of the drug will be ionized. Ions cannot be reabsorbed and therefore excretion of the drug is enhanced. Alkalinization of the urine can be achieved by administering an alkali like sodium bicarbonate. Let's summarize the renal excretion of drugs. Through glomerular filtration and tubular secretion, the drug and the metabolite from the blood reaches the tubular lumen. A fraction of this undergoes passive tubular reabsorption to return to the capillaries. What remains in the tubular lumen is excreted. Here is a good to know fact.